Hey, nice to meet you all. Again, must say that I still didn't get to the grading of the work, but still, like the good news is that another university course that I'm running will end next week, I think, and then I will have much more time to properly evaluate what you have done so far and give you some comments. But today we'll do some kind of interesting tutorial. So please get the template. So the template 7.2, I think it was. Let me quickly try to check what was the name of the template that I added like a few moments ago. The template 7.2 from the Google Classroom. Please get it and post in the chat that you have it. So template 7.2 ready for work. So plus minus if there is some problem in the chat, please. Meanwhile, I will start sharing the screen as well. So just to remind you, we're still working with contrastive loss, the hinge loss, like one of the hinge loss variants that we looked a few sessions ago. And we'll also have the today the semi-hard and hard mining problem. Like it's actually a solution to improve the like training convergence, and also we'll look at the accuracy calculation using the clustering as we like looked at various clustering methods for past few sessions. And then like next week, probably we'll start moving towards direction of the triplet loss and other deep metric learning methods. So today actually the FaceNet paper that Aiga was asking to give some references is from 2015, and I think it was the first time when they introduced this kind of technique just to improve the learning process of the semi-hard and hard sample mining. By the way, that again, that just tells you that there are so many things to do in this field. That like only 5 years ago they kind of published their work with really trivial and kind of like it's not like well, groundbreaking science, you know, like you can invent your own probably sample mining methods. You will see today that this one is really a simple one, but you can have like even better ones invented yourself, publish the paper, get the PhD and stuff like that. So, I mean, like this is a good time to be working with deep metric learning. So in the paper, if you look in the paper, we see two constraints there. So the one is in the equation 1. So the constraint in equation 1. So I will drop that one in here as well. And so that is the hard constraint. So you already know this notation. We already talked about this notation a lot. So this is hard constraint. Maybe I didn't, hopefully I did not misspell it. Yes, and the hard constraint just tells here, if you look at this image, so yeah, I will just explain over hard. So we look at this image, we have the situation where there is an anchor point A, then there is a positive sample. Basically, by the way, here the positive sample, at least in this case, it's kind of like determines where is the margin here. So this will be then calculated from the most positive sample in the distance, or it depends on how you look at it. But basically, normally it would be from the anchor point if they are both from the same class, right? So they are same class samples. You want to look at the A this middle point of the same class cluster and the farmost point, but in generally, like also today, as we will code it, they are just like on the first come basis. Like the A is not actually the cluster center of the same class. It can be all sorts of pairs here. So these are the positive pairs, and then the negative pairs. So if the n like sample would be here, so that would be easy negative because it's already outside the margin. So we want that the classes are separated in the embedding space by this orange margin. So they are already outside of the orange margin. That means that they are easy to separate, easy to learn, nothing harder. So when the negatives come in this margin area, so that is already some problem. And then the hard negatives means that they are mixing between between positives, so that maybe the negative is closer to the anchor point than the positive. As I say, so this notation is more like a triplet loss, where we have always for every sample we have one positive and one negative sample. Today we will use this notation only in the part of the mining procedure, and it will kind of produce actually the triplets. So we will work with the triplets using the contrastive loss. That is something that you can do, and I have not seen actually good paper where they compared the contrastive loss with the triplets and the triplet loss with triplets, and there are also tuple loss and all sorts of variations of this. So I mean, this is just one step towards more advanced techniques. But again, so the hard samples are those that are below the range of the positive distance between same class samples. So this is different class sample, this large one that I draw. So it should not be here. This is hard because it should not be here, and the model thinks it should be there, but it should be pushed out of here. It should be pushed out of the semi-hard area into easy area. Is it clear so far regards to this notation, or something not clear? So is it clear? Plus, minus, maybe some comment if minus what is not clear here. So again, we are talking about embeddings that you get from the model. You pass the input image or whatever, like face or any sample, you get the z vector, and then we calculate the Euclidean or cosine distances, and we have the positive pairs and negative pairs. And if the negative pair is in this case, so I understand the hard thing, but I'm struggling with the notation. So the notation here, so these two lines with this kind of notation, usually it means that is the square that is the Euclidean distance, like because so let me think. You could write it probably just with the squares or whatever, but in the sense that like this can be also cosine distance, this can be also Mohanovi's distance, this can be also what else? There are quite a few other. So the ones that we are actually talked last time. Remember the HDB scan? They had the custom distance metric, right? So this notation can be even some kind of algorithmic custom distance metric. So yeah, L2 norm, right? Yeah, that is L2 norm in this case, and that is the same as Euclidean distance in this case. It could be also L1 norm, by the way. I think I've read one of the Kuhn's early papers where he used L1 norm. So that would be again different result. Also, it could be probably Manhattan distance. There, Not sure like would it be good, but still. Anyway, so this is one. So then the next one is in that same paper, equation number 4. And that is what they call semi-hard constraints. So they have two constraints, semi-hard constraint. And if you look at this one, so the both must be true in order to pass the backprop through these samples. If they're not both true, then we drop those samples out. So they are basically, we are mining, we are looking for the best samples. So here, what it means, so the distance between the positive pairs, so the negative pairs should be like larger than the distance between those positive pairs. So that means that we are now looking only at the yellow or orange area. So if you use both of them, and the idea is that they are arguing in the paper, if you use only the hard constraint, there is a probability to have the mode collapse. That means that everything is collapsed just to the point A. Like there is all of the distances between the positive pairs are like close to 0. And that is not optimal situation, because then, for example, if you have one class cluster here, and if you have another class cluster here, I'm not like, it's probably will be hard to understand, but hopefully at least in some capacity. So probably when you will work with this a little bit more, you understand it better. So let's say we have two classes. So this one would be, for example, class 1, and here we have some kind of class 2, right? And if we got the mode collapse, by the way, that happens also, I think, in GANs as well sometimes. So what would happen is that all of the positive pairs would be collapsed closely together here and here, and in between here, there would be nothing. And what it means is then if we pass some new sample that was never seen by the training, it would jump either here, either here. It would not be like, okay, this person is similar to C1 and C2, but not really C1 or C2. Maybe we should place him here. But in reality, it would just jump around from modalities in the embedding space. So that's kind of one of the ideas why they use semi-hard constraint. But there are, again, other techniques how to do the sample mining. And for the homework, I will give another technique to implement. And you could even implement your own IDEs. Like if you implement your own IDEs and you get nice results, that would be even better. So that is the idea of the mining. It means that that you need larger batch size, and then you will reduce the number of batch samples, just leaving those that are good. Okay, so let's move back to the code now. As you indicated that you're ready to work, so let's do it. So if we go here in the code, this is the same template that we worked before. It's a little bit added, like some like naive calculations of the accuracies and stuff. But here I added also sample mining procedure. So the sample mining procedure, if you look at sample mining procedure, okay, the template link, right? I will drop it in the Mega as well, but it's in the classroom as well. So just a second. So I'm trying to copy it. Or you could not. So let's see. Okay, fine. Yeah, got it. So I copied the mega link as well in the chat. Anyway, yeah, so we have the sample mining procedure here. By the way, I also added here, I forgot to delete it because I wanted to ask you this, but basically you need to check that you have at least one pair that you would train it. And also probably for this kind of situation would be better to use the mean loss function. As you know, that there is no problem of using some loss function, but because we have the constant learning rate, not adjustable by the batch size, that's why it would be much better to have the constant so what I mean is that if we have like mined, let's say 18 samples or 6 samples or 3 samples, we should have the same kind of direction of the learning, the speed of the learning as with a larger batch size. And if there is no good samples in our mining procedure, then we just skip them. So what I mean by no good samples is that hopefully that means that all of the classes are well separated. But in the case of semi-hard like mining, there is a chance that they would not be actually good separated. Like if, for example, if the two classes are really similar, they are both under so they are both under the curve, under this radius of the margin. Anyway, so let's go to the sample mining. So we'll try to help you out with this procedure, and then for the homework, I will give you another algorithm that you can implement, or you can invent your own sample mining procedure, because there are a lot of, so there are histogram-based sample mining, there are like some kind of something, so the easiest one would be some, what would be like, I don't know, like the most hard sample mining, for example, where you just look for the sample that is the closest pair with the anchor, where there should not be closest pair, like the separate, like different class samples, but they are very close, the closest one, and then you would just use that one. So, and then you would use the opposite for the positive ones, the positives that are the longest distance apart. So that would be another technique. So you can invent your own as well. So anyway, here, let's say we will have the anchor Z's. So what I want to do is to not make it everything too complicated. That's why I will try to split variables in many parts. So maybe even the code can be much shorter, but I just want to make sure that it's trackable, so you understand why something is split in places. So here Z will be up till anchor point. Again, here this is a naive technique. I'm just taking the first anchor size element. So the anchor size is batch size divided by 3 in this case, because they're going to be kind of triplets. But smarter thing would be to ensure that your, like let's say what's here, the data loader would always provide like the situation when you have the anchor from the same class, then the sample from the same class for the positive and sample from the same class for the negative, a different class for the negative, and at least they maybe two of both of those situations. So you would have always 3 samples from the positive and let's say 3 samples for the negative, and then you would choose from them. That would be much smarter way. Now we are using very naive way. We're just selecting from the random samples here. There could be a situation that samples are from the same class multiple times. Again, not optimal situation. So definitely could be improved, but I'm just showing the concept here. So then the other, so O will be the other. Maybe I should just write it full, otherwise it will not be understandable. Anchor. Hopefully that's correct. Let me check. maybe misspelled it. Right, it is correct, anchor, then these will be the other samples. Other will be those that we want to mine and match. So these will be these. Other Z, other Y here. Then the distances, torch C dist. So the C dist is an alternative way of doing this with the pairwise distances, just avoiding one loop here. And if you look at the C dist inside, you see that there is a compute mode that is Euclidean distance, I guess. But in general, like you can choose it. Probably it can work with other distance metrics as well. So anyway, here there is then the anchor distance. By the way, if you want to just calculate the Euclideans between themselves, then you can use p dist. So there are c dist and p dist. So you're looking at the embedding vectors, trying to calculate the distances between them. That's first. So let's go to the next, and the next will be the, let's say, anchor and anchor I. So we will go by indexes. So there will be a first loop here. Again, some of the things can be written a little bit like shorter, but trying to show the point. So going over anchor Z here, then go. So don't worry, I will also try to drop some of the snippets if it works in the Jamboard. If you cannot get ahead, but hopefully you can. Again, trying to remind you that probably there are some tools like the picture-in-picture tools that you can use in your computer, so you can watch the video and code at the same time, or if you're lucky, you can have the second monitor. So the second monitor is be great. So all of these kind of studies work much better like in person, when you can see that on the screen, and then I can check the speed of how everybody is doing. So sorry for maybe going too fast. So anyway, so there will be then the positive indexes, positive i's. So here there will be the anchors of the, so the anchor I, where they are the same as O other Y. So I need to also explain. So the distances, this shape will be D. So it should be the shape of anchor. So the length of anchors. Of course, now we are ignoring the embedding distance, right? So embedding dimension, because after the distances, it's just a scalar, right? So the anchors and then the comma others. So this is the shape of the distances. That's why I can do this. So I selected the first row for the first sample, and then look where we have the matching classes. And the matching classes means that these are the positive samples. And the classes that are not matching, these are the negative samples. So that's good. Then the next thing, again, again, probably can be written shorter, but I just want to make sure that all of the variables are listed here. So the positive distances, positive dists, these are then from the dists where there is an anchor I. So we select the row, and then we select only columns. So the pos I. And the same for negatives. So we have the negative distance, positive distance. So now we are already, so these two variables already are the same variables that we need for the equations on the Jamboard. So that's great. So far, good. Then to make our lives a little bit easier, because otherwise, if we just work with these directly, we are already like changed the shapes of the distances here. We already don't have the same shape as here because we have selected only the positives and negatives. and then we'll need to trace it back to the correct indexes. That would be really not nice. So let's try to use something different. Like we could also slice out the z's and the y's. So pos z will be the other z of pos I. The same for y's. I'm doing this because the shape right now after this operation of pos I or neg I don't know what is the shape, because it's possible that there is no samples matching at all. It's like zero shape, or maybe there's like all samples matching or something in between. So if I would use then try to select something directly from other z, then I would need to go through this array or the vector of pos I, and like I don't like it. It's better to just like slice it. So here there is then it's easier to debug, definitely. So neg like that. So I'm just selecting all of those out. So that's fine. Then the next one, maybe that would be good, is to use some kind of is found, some variable, because we will have we'll need to look all combinations between the positives and negatives. And again, here there is a room for improvement. We can look for the best combination, like the kind of the worst combination, because the worst combinations are the best for the training. But now we will just take the first combination that is matching. So for, let's say, so there we can use the, let's see, pos I in range. Oh no, I already have pos I. Okay, let's use G in range of len of pos distances. So again, must emphasize that this vector is not the same shape as this vector, because in this vector we selected out only those elements that are true in pos I. Okay, so this will be the first iteration. The second one, k of negs. That's one. That's two. Then we can start by working just with the negative constraint. So pos distances of j plus margin should be lower than neg distances of k. And then we can say it is found true, and we can break out of this loop. By the way, also we can break out from the next loop if is found. Probably, yeah, but we cannot break from the next, the last loop, because the last loop is then important for the that we need to look at all of the anchors, not just the first anchor. So okay, that's fine here. What else is missing is that let's define some return variable. So I will copy the upper part in the Jamboard just in a second. Return z, maybe let's call it stack z, so you understand that this is just a list of z's, stack of y. So these will be ones that I want to return from this function. And I will, as I say, because it's possible that these will be empty as well. So, okay, let's add the upper part from line 103 up till 111 to the Jamboard. Slide 2. Oops. So that's added. So then the lower part I also will add in a second. So here, when it's found, it means that we can add to those stacks. So stack z, we can append. And here you will see what I mean by triplets. So we append the, the anchor z of anchor I. Then we will append, by the way, we could just use all of here, just the I, because we have JK here. Okay, just to make code a little bit cleaner, I will refactor, but you can keep using anchor I, by the way. So, so I, like that. Yeah, so the anchor I here, then the positive Z's should be then selected by J, because there's a J loop here, right? Then the negative Z sample should be selected from K. And we add them all to the stack of Z. So here there is a first triplet that you have worked with together. Like, so I mean, it's not just the random pairs of positives versus negatives. Now it's like a actual triplet where we have the positive and negative always. So that's one. Then for the Y's as well, because we need to somehow indicate if they are from the same class or from other class. Otherwise, we cannot, like the outer function will not know this. So you can use it like that. Hopefully that's fine. Anchor Y, yeah. Okay, so this part is also ready. I will drop this into Jamboard, like this block of code from 113 up till 138 line. So this is the hard mining, not semi-hard. Semi-hard is missing the second constraint. You can add it later. To do add semi-hard constraint. So that's one that you can do yourself. That is not difficult. Then then here, let's say you can look the equation up in the slide. So then the Z here, torch stack of the stack Z's. And then also let's stack the Y's. Okay, that's great. So, okay, I will probably update the Jamboard again with the whole code like that. And then I will check if there is no bugs. If there will be bugs, I will be forced to update Jamboard again, but hopefully not. So let's see. So if I try to run it, let's see what I have. So first of all, I will not train it fully. Okay, there is a problem. I will check it, but I will not train it fully because there is the limit of max lane up to 200 because I have CPU. On the GPU, there is no limit. But if you have GPU and you want to debug, I would suggest that you add some limit there. So the bug here is in this line, too many indices. Maybe I messed up something. What did I mess up? So too many indices for tensor dimension. That is a strange error. Okay, let's check it. I will add the breakpoint. That's why it's great to not have too big data set and the batches for the testing, so we can check it, the breakpoints. Okay, what is that? Okay, the breakpoint didn't work at all. Strange. Let's see. So I is 0. That's great. These are okay. That is strange. Other. I definitely messed something up here. So the anchor Y, that is fine. Yeah, there is a bug here, I guess. Shape 58 by 32. That is weird. Yeah, I see the bug. So in the first lines, nobody noticed that I misspelled one letter here. Other Y equals Y, not Z here. Usually somebody in the course or like your students notice things like that, not this time. So I beat you this time. So let's see. Yeah, because like if you write the code carefully, you definitely see you're writing like other y equals z, something not right here, right? So that's something that we should fix. I will add the colored version in the Jamboard. If you see something strange in the code, most likely that is not by design. So that is probably a bug then. So if I try again, so the shape now looks a bit better. It selects some of the elements there. If I run it, okay, but still something is not good. Okay, do we have another bug here? Yeah, that is reasonable bug. So this bug just means that it's possible that there is no good samples in the batch, and we cannot stack empty vectors. So here, then I guess what would be a good approach? Let's see, if len z is larger, then we can use it like that. If not else, then probably we can just return empty lists, because in the training loop I have a function that just like checks if that's an empty list and then not use it at all. So, but still, it's kind of interesting that it broke down there, because I think in very beginning it should not be a situation that all of the samples are bad. Maybe I have some other bug here. So let's see. Can I get any sample combination where there is good sample combination? Yes, I got one. So that's good. There is a multiple. And the stack here, 18, the batch size of 18. So that's great. It works. So in general, it works. Maybe because I have only 200 samples, I very easily get the situation where there is no good training samples at all. See, it kind of gets to the point where there's no good training samples. The accuracy, the accuracy is not something we should look here, because it's only 200 samples. It should be then done with a full training. Okay, so this is the part of the sample mining. Okay, your semi-hard sample mining you can do yourself. I will like some other ideas how to do this. You can do also yourself. And for the homework, so this is very important area of research, like the sample mining for the deep metric learning. That is something that you can do as your research for the master's, PhD, and stuff. So that's a good direction. So then the next one here is for the clustering. As I said, the one of the state-of-the-art approaches is to use the PCA whitening with the spectral clustering. And we already learned how to do the spectral clustering, so, and the PCA as well. But here there is a situation that we cannot really do the kind of spectral clustering over all of the possible samples, because if there are like 80,000 samples, the no memory would actually hold them as in the matrix for the spectral clustering, right? So it should be done incrementally or with the batches. So for the batches, I think the best way to do this would be using the k-means clustering using batches is possible, because you're tracking just the centers of the clusters, and that is something you can track the same way as we did it here in this code, but just for the clustering purposes. So that's one option. So for that option, you could use, maybe I could add that as a homework. You could use the sklearn cluster mini batches, and this works with partial fit. So it means that you can call it many times and fit the clusters like without remembering the previous samples. They just accumulate the centers of the mass the similar way as we do. Basically, if you I cannot use actually like fully the spectral clustering of whole data set. That's why that's one option how to do this. So the other option is to do this for every batch. For every batch, again, it depends on what kind of clustering algorithms you want to use. In this case, let's use the spectral clustering, and you could add a PCA whitening yourself later. Again, that's not something too difficult. We already investigated it. So here the Y CPU. So we need to know which classes it belongs to. Otherwise, we cannot even. So we need to now know some ground truth. That's one. The other thing is, depending on the clustering algorithm, if you remember, some clustering algorithms need to know K, how many clusters there are. Other clustering algorithms do not need that information, like HDB scan, but it needs some other information. So anyway, here we'll try to use spectral clustering that that needs to know how many clusters are there. So there is a one special case of spectral clustering that is very beautiful. That is when you have the just two clusters. That is the best spectral clustering property. So if by any way you could reduce your deep metric learning task to separating two classes, that would be perfect. But in this case, we have 10 classes. So let's use this one. So I'm just reminding you that we explored that property of spectral clustering, and that's quite amazing. So here there will be the MPY unique. Again, quite important to know how these algorithms work, the clustering algorithms, otherwise you don't know how to control them, and you assume that something works, but actually it doesn't work. So here there is MPY. So what I'm doing here is trying to find out what is the K for the clusters. So number of clusters. So clusters K, and this will be just the length of the unique Ys. Again, the procedure how it's made now, it's a very random procedure. Like if you could make a lot better sample mining, a lot better data loader, that would always give you like predefined number of the clusters or the same classes every time you call the batch. That would be a better way. Here there's like a lot of randomness here. That's why we need to even calculate how many clusters are there. So that's one. Then we need to move the MPZs as well here. So Z CPU data numpy. So the ZP, so the Z's are the embedding vectors, right? So that hopefully you remember. So then let's see. We have these guys, so we can do the spectral clustering. Spectral clustering, I think it was like that. So import sklearn cluster spectral clustering. I will drop this also a little bit lower here. Just a second. I did import it. Why didn't it show up? This is weird. So sorry for scrolling. I will fix it. Okay. No, it shows up here. Okay, I didn't see it. So of course you need to import it from here. So import from here. Right, so that will be the spectral clustering. The spectral clustering wants to have the N clusters gamma. So the gamma is for the radial basis function that I don't like here because it will just make more nonlinearity where it's not necessary. Okay, so let's see. So there will be the number of clusters. So that is the n clusters. You actually could call it like that. Let me rename it here, n clusters. Then, sorry for going in here, I need to just check it. So the affinity matrix should not be RBF. At least I don't like it. I want it to be a linear one, hopefully. The worst case scenario is that then I just need to calculate my own covariance matrix. But I think there should be some way to set it. To do, if somebody knows I think you just need to call it Euclidean, hopefully. We'll try it. Spectral clustering affinity. Okay, let's see. Is it affinity? Yes, affinity. So, by the way, the first one, okay, that's an clusters, right? So, by the way, I'll better write it like that because I don't trust the order of those. So affinity would be then okay, do I want to have a Euclidean here? I'm not sure about that. Okay, we could use Euclidean. So that would be a linear method. So that's not really the spectral clustering using the covariance matrix, but still it's better than using the radial basis function, definitely. Radial basis function would make it non-linear, and we already have non-linear model. Combining two non-linearities here is not desirable. So then the clustering, so that will be the algorithm. Then the fit predict of the NP Zs, and there will be now the NP Y prim. So these are our kind of cluster predictions. Now there is another problem because the cluster algorithm do not know actually, like, so the indexes would not match between NPY and NPY prim here, because the clustering algorithm, of course, don't know that index 0 means that there is a shoe, and index 1 means that there's a trousers, index 2 means that there is a like shirt and stuff. So we need to somehow resolve this problem. So this will be the not really NPY prim, but NP. Let's see. What could we invent here? NPK prim, because that's a cluster prim, right? So you need to convert NPK prim to NPY prim. So that will not be super easy. Like, if you have better ideas, you can let me know, but we could try to find where they overlap most. So find most overlapping, find most overlapping embeddings, Z's, and yeah, and so we'll have some kind of matching dictionary probably. So let us see. So so we'll go one by one there. Okay, so K to Y, there will be a dictionary here. For, by the way, again, okay, we already know that we have n clusters. So for K, again, if you use HDB scan here, we don't need to know then the n clusters, but it's possible that we would have noise. Also, there are some clustering algorithms with n clusters that work with noise as well. So the noise is a separate class of clustering. That should be kept in mind. So range. By the way, of course, here to do PCA whitening, that you can also already know how to do that. So here there will be the range of the n clusters, the case. So we go over case and look for the most overlap between npk prim and npy, and that's how we assign the y values. So let's see. So there is a k now. So we need to get this will be the k. I should have thought about this before a little bit, but I definitely can invent algorithm now. Just a second. So we should select out the elements from the npk. So there will be maybe I will delete something in a second, but I will try out. So np idxs prim. Where these are selecting of k. So these are the indexes of k prim. Probably I need to log the maximum number of the samples that overlap for each of the y's. So this will be the k. K. Maybe I should construct some kind of matrix. Let's construct maybe a matrix. So k by y count. This could be np zeros of n clusters by the n clusters that I know already, right? And the n clusters as well, because that will be the y's that I have here. And then I will select only those that just like step by step select those that are the most common. Like so I don't want a situation that I first select 1k and then choose the assignment before looking at other k that might have even more overlap than the first one. So here we can go over this one. Then we could probably go over the y's. So let's see. Y, I mean, let's call k y's again of the, okay, k, maybe I should just call them, this will be j, and this will be k. So, well, no, I don't like it. Let's leave it as k and j, sorry. So, because the k's are the clusters. So, the j's here will go over the npy's. So, idx's of the y's will be the npy, where they match the j's. So we have these guys here like that. Then we need to calculate the overlap between both of them. So overlap, by the way, I'm coding this on the fly, so hopefully it will work fine. So even didn't have time to properly think about it. So k prims where they match, the overlap sum. So this is the overlap, and or basically the scalar, kind of like which one is the most likely cluster for which class. So then we insert that one inside the matrix that we have here. So that matrix goes by K and J, and we insert the overlap sum here. Or maybe we can just call it count, because that's the kind of the same thing, overlap count. So we inserted that one. So now we have kind of the our Rosetta Stone ready, basically the kind of translation matrix where we can start trying to get the sense of the matching. So we should then probably look for the maximum overlap between the classes and remove them one by one, probably. So let's see. We'll definitely have k iterations, because it cannot be more than k iterations, definitely. So then we want to have the np argmax argmax of the k by count here. So the argmax will work on the dimension 1 probably. But the problem is that I want over whole matrix the argmax. Just the for the testing, if everything is okay so far, I will try to run it, and we'll play around a little bit with it. So debug it up till the line 277. I hope that what I'm doing makes sense at least. So okay, there is the the pairwise distance something. Okay, Euclidean unknown kernel. Maybe linear should be correct one. Linear. Let's see. Well, that's a CPI implementation. It might be different. So okay, here what is okay? I guess wrong notation. Yep, this is a wrong notation. There should be another brackets here because that's the shape. Yep, so we can add even the name. So here shape should be like that. Okay. Okay, my algorithm so far works. So the matrix looks like this. So if you look at this matrix, so there are 9 classes, and here if we look at, so we are interested at, so we can actually do this just by one call, so that's great. So we are interested for each of the classes the maximum. The problem is only that we also need to do this iteratively, because some of the maximums, as you see, the 59, 59 are the same for multiple classes. All right, so let us think. So the K, so okay, NP argmax of the K by Y, axis of 1, of course, that one what I'm interested in. Axis 1, what is that? Okay, wrong parameter. K by count. Okay, now we selected the best ones from those classes, but they also want to know the numerical values. So let's see, I think there was one function that also gave the they gave both the indexes and the maximum values. There was one, so max probably with this one. These are the maximum values. Okay, but still, we just need to do that in twice, so let's do it in this way. So, okay, got it. So first, let's get the max values. So these will be the counts by class, and this will be the axis 1 counts by class, and then we'll use the maximum of those. So there will be the let's see, K max cluster. That will be the MP arg max of these guys. And now we kind of selected the max cluster. Now we need to get the actual Y value. Counts by class, right? That's a K max cluster, right? Y Y assignment, but okay, so here as well, that is assignment actually. So Y assignment then is the MP argmax argmax of the counts by class of the K assignment. Oh, let me think. Was it like that? Maybe I messed up. So the K's are going by the rows, right? That is correct. Y assignments are the columns. That is correct. So that's great. So now I got the assignments. So here, then the K's to Y's will be the K is Y assignment. The last thing missing here is that we need to eliminate now that line, because the other iteration cannot collect the same value. So what I can do is to have this line set as the float minus infinity. By the way, this is the same method as they use in the attention models for the softmaxes to like mask them. Just use the infinity minus, so like that. Hopefully this algorithm is ready so far. I will add also the first part already to the Jamboard, so you can follow up. So the advantage of using the clustering techniques for the calculation of the accuracy is that at the end, when you will use the model for the unknown samples, it should work well with the kind of clustering properties, depending on what kind of clustering you use. And just the simple radius method or this closest sample method is not powerful enough probably. So here to estimate the real accuracy. So this part is fine. So we have K to Y mapping. Now probably we just need to now produce the Y prim vector. Okay, let's do that. So MP Y prim will be MP array produced from the list. So in the list we can produce it in this manner, where we select the K from K in NPK prim, like that. Now we have proper Y prim vector, so like that. And now the actual clustering accuracy is like trivial stuff, so the same as always. So NP mean of the matching of the NPY with NPY prime. Hopefully that works so far. If it works, I will drop it in the Jamboard. Like my algorithm using the matrix of the distances maybe could be improved. I just made it up on the fly, but hopefully it's good enough. So what's here? Something it doesn't like. Decay, what? So some kind of assignment missing. Interesting, let's check it. So the M clusters should be 10 clusters, right? That's good. Then the counts by classes, that's the infinity, that's also correct. But the K assignment somehow got it wrong. K2, Okay, I need to double check this part of the code. There's something not right, I guess. It should select like the best values by maximum. And somehow it selects the same value for all of them. That's strange. So, okay, the assignment is 0. The K here is 4. Okay, that's the first run. The second run. Okay, I guess maybe my problem is that I'm using here the axis 1. Yeah, definitely. By this definition, this should be axis 0. So that's one problem, probably. Let's see. Okay, now it's good. So the K is 7. Okay, there is something definitely not good. Still something is not right. So okay, this is the matrix. What is wrong with that matrix? Okay, I have the wrong assignment here. Yeah, let me check again. So the maximum by the axis. Okay, no, it should be, I think so yeah, it should be the axis ones here. But the problem is that here the K by count should be nullified. Okay, let's see again. Use the temporary variable there, but it should just change the matrix itself. Okay, the first one 6, second one 7, 5. It seems like it's working. And if I look at the matrix, okay, see the minus infinities are propagating that I want. Hopefully they are propagating in the correct order. Anyway, so we can double check that later. So that part works. Then let's see the next part. I will update also in the Jamboard that lower part of the code just in a second, if it works. So the accuracy matching, except the NPY prims, all are zeros. That is super strange. NPY Ks are definitely bug here. So the Ks are like in this pattern. So that's good. And these are definitely not good. All of them are zeros here. I guess I had the wrong assignment here. I needed to nullify not these guys, but these ones. by the columns, not by rows, but by columns, because the rows are unknown assignment. Let's see, will it work now? Okay, there is a problem now. That is strange. Okay, need to debug this again. I was not expecting that I will stuck in this part of the code. I would be more expected to stuck above or in the other part, but still. Okay, so the K, okay, the K counts. So we can actually check it quite easily. So if you look at this matrix and compare what we got by the counts by class. So if you look at so I have a typo. Maybe I have a typo, but I think there is another bug. MPK K to Y, MPK prim. No, I think it should be like that. Okay, you had the typo, right. So it should be like that, but here there's definitely some other problem. Logical problem, most likely. So let's see. So we have 10 classes. It's been easier to check. No, it did not change. So then the 10 classes, there will be then one is 62, first line 62. Right, the 62 is the largest value from the first line. From the second line, 36. That is the largest value from the second line. 61, largest value from the third line. So this part works as expected. It gives me the best value from the columns, which are the assignments for the y's, and the k's are in the random order in the rows. So I got those. Then I get the k assignment, which is the column with largest value, which in this case, like in the random order, is the first one. So that is good. Then I get the y assignment, which is also good. So is it good actually? So the counts, okay, here I have a problem. It should be k by count here. Okay, I got one bug fixed. So here again, this should be k by count. Yeah, it should be k by count, not by counts by class. So that will, then I will get the y assignment. Then I would need to eliminate all of the y assignments from that matrix, and hopefully now it works. But I wouldn't call it yet. Let's see. Before I also thought already 2 times that it will work. So, okay, let's see what I have here. So this is definitely not good. It still have like only 3 assignments, which is wrong. So what gone wrong here? So the infinities are everywhere, which is interesting. The argmax by counts, that's fine, but this line should prevent it happening that the y assignment is the same. How that could happen? Something strange happening here. Let's double check again. Almost ready. Something is still missing here. Okay, again, so the matrix like that. So the k's on the rows, the y's on the columns. So the count by class, 57, 59, 61, somewhere in the middle, 0, 1, 2, 3, 4, 5, fifth line here. So the fifth line, 61, that is correct. So here, this column, oh man, I order it somehow. Okay, this is not what I want to do. So the 61 line like there, so that is, except I need to check it. Hopefully it is will be refreshed. Okay, yeah, it is. So this line, the 8th column should be infinities, minus infinities. So the 8th column assignment, right? So let's go to the next iteration. Look here, minus infinities. That is great. So then the counts by class, again, now we get the okay, I should also eliminate it both ways. Sorry, got it. Interesting. Somehow when I was thinking about it, didn't notice it. So I should eliminate it by the y-axis and by the k-axis, like that. Right. So that now the actual visual would be more interesting even. It would make those cross sections all the time. So let's see. So if I run it once, it looks like that. So I eliminated all of the assignments to the 5th and also to the assignments to the K3. So it should not use those anymore. So if I try it again, now it eliminates this one and this one. Now it seems beautiful. So let's see. If I get here, now I get proper assignments. Again, this is something that definitely needs to be checked always by debugging, because otherwise you think something works and actually not. Okay, so now it works also here, and the accuracy is 28%. So great, it works. I will drop this into Jamboard. So this algorithm turned out a little bit more difficult than I was expected initially, but I think mathematically it's interesting, as you see that you can use the matrix for storing all of that information, and use the MP argmax. So this part you can improve it as well. So for the homework, I will give you another mining technique and another clustering technique here. And next time we will look at the triplet loss. So that's it from today. Hopefully it's interesting and hopefully not too challenging. So I will keep track of the works that you submit in the Google Classroom. That depends for this project as well, that you should be successful in those works. And yeah, so let's meet next week. Hopefully it was interesting and useful, and hopefully you will be able to complete the homeworks. Okay, bye-bye.